Okay, we're recording right now, so the tradition, also the way this works is, this is Camtasia Studio, which I used. I think Dr. Trimboli uses it, or used to use it, Dr. Platt, because the three of us were the systems faculty. It won't get produced right away. It takes some time for me to produce it from the raw material, the MP4 file, and then I will edit it, and then it will turn into looking like the video that's already up there, and then I'll have to create another channel, I guess, for Fall 25 on YouTube. It'll take a few extra steps, but I'm doing that because maybe somebody else will jump up and say they want to take the class, and this way I can just say, look at the video. You'll know what I told all of you guys, so you'll know. So we'll get started, and then we'll have to stop right away because I'm definitely not used to 75 minutes anymore. I used to do that, but we'll see where we're going to go with that. I want to do some of the overviewing stuff before I actually get into looking at the schedule and how we can make this work. So this website is the home base for the class. Everything is on here and then some. This actually maintains things for other people. I like the material so much that I've been sharing it for all these years with the world, and people watch it from other places, ask me questions. I have the Signals and Systems for Dummies book, which I didn't bring with me. I wrote that. If you haven't heard of it, it's out there. I don't have it. It's on Amazon. Signals and Systems for Dummies. It's referenced on some one of the documents. Why did I write the book? It's because they came to me and they say, we would like you to write this book, and we're going to pay you to write it. Have I made money on selling copies of the book? No. It was a lot of work, and I didn't. It's like anything in life that you might agree to do. First off, it was intriguing. Somebody wanted me to do this, so I had to try out for it by writing a sample chapter, and then I got accepted, and then immediately I was on the hook. I signed a contract, and then I worked and worked and worked and worked, and I got paid a certain fixed amount of money, and the more you work on a project, and if you've done a project for somebody before, you know if you get a fixed price and you work and work and work, what happens to your rate? It drops. It dropped down really, really low. I think less than $10 an hour probably, which in the end seemed pretty daunting, but it was a good experience because it led me into Python. So I'm going to give you these two. I already wrote a note on there. And I want you to sign in. And then I'm going to stand here because I want to see if you're this is the lecture. This is the lecture, and then if you're taking the lab, I just want to know if you're taking the lab. Okay, so you're number 6. The 5th person. Everybody else in here knows from the emails that went on last night that there was a 5th person that asked for permission to take the class but has dropped out of sight. So you just are what I'd call a walk-on. In sports, you're a walk-on.
Yeah, okay.
Which is fair.
He's a walk-on.
Yeah.
We're on scholarship.
Well, who's the athlete? Okay, so you know that term.
Yeah.
What sport are you in?
Soccer.
Okay.
Yeah.
My son did. At CSU, he tried to do a walk-on in track or cross country, and it just totally destroyed him. All the hours spent running. He dropped back his course load, and it changed him a lot, and he gave up on it eventually.
Yeah.
But he ran really well. It's just really hard to be a walk-on, though. Okay, so getting back to what I was talking about, for Aaron, at least, you don't know because we had an emergency email session last night. And I'm going to need your email address, too, so I can get you on Slack.
Okay.
Actually, I'll just put that up here right now. This is our Slack channel. for Modern DSP, and three of you signed in. One hasn't accepted yet or hasn't taken the time. Okay. So I'll get you on it too, because it's going to be important as we look at time changes. Because right now, I was planning on teaching it on Wednesdays in the morning. I had worked all the channels to do that, and then it never really happened. So we have to come back and revisit that later this morning. I have a feeling, though, that just because it's going to take time to put the wheels in motion, it's not going to happen by Thursday. It would be a miracle. So I think we'll have to plan on coming back tentatively. I'll just say that right now, tentatively, we'll be coming back to 8 a.m. on Wednesday, or Thursday, I mean, just because that's on the schedule. I can't void that initially, because we all have to agree on it, too. That's the other thing that makes this really sticky. But like I said already, if I disagree with it entirely and I force the class to be shut down, then that's what happens. I mean, there's nothing I can do about that. Okay, so I was back to the website again. All the information is on the website, including lecture videos, and this newest video will be put up also in due time. So you get all your course notes, homework assignments, and so on are on here. For example, right now I don't have the Set 1 homework assignment on here. I have one from last year, and I'm thinking of sticking with it. I'm thinking of just changing the first problem because it's kind of abstract and has been challenging in the past. I have a demo that talks about how to work some of the problems. It's done in Python, because a lot of computer modeling tools are important in understanding the math. And being that right now, well, ever since I left here, I've been working in industry in DSP and comms, and I've done that up my entire career. So right now my position is exactly what this class is about. I'm doing DSP every day, and I'm actually using Python to model everything. And probably my team will be trying to contact me this morning because they didn't know I wasn't going to be available on Teams in the morning. And some of you are doing internships. The team that I'm on is all over the country, so there's people on all 4 time zones that I'm working with, which is challenging at that. So the guy that I've been working with yesterday he's in Connecticut. He's an FPGA implementer, I call him, and I'm a systems architect, systems level designer in DSP algorithms. So what are we doing? We're testing hardware that's supposed to have been delivered weeks ago and doing exactly what this course prepares you to go off and do, and that is do your modeling and simulation and work with implementers and see that things get done, and then go back and forth on stuff like that. So I was looking at, did I already have hints up? And this particular problem, because it was the first set from last week, all the hints are available, but like I said, I'm going to change problem 1 most certainly, but I'm going to keep the others is my thinking right now. So that's there, and that's not there. That's the solutions, and these are the old solutions, but that's giving you a tour of how assignments and things work. Is I'll put up an assignment. Frequently I'll make the hints page come up a few days later so that you have to actually be studying it and then get excited about, I can't figure this out, I want some help, so I'll give some hints. And then after it's been turned in, then I'll put up the solutions, and then I'll be grading it on my tablet. So we'll be using Slack for you to turn in as PDFs your homework papers, and then I grade them and mark on them, and then they get pushed back on Slack. So that's from the earlier question about Canvas or Blackboard, or we're using Canvas now, I guess, on the campus, right? We've used Blackboard and maybe a few others over my lifetime. That's my course management system, and I'll just defend Slack a little bit more by saying Teams is great. I use it all the time at work. It's like Microsoft Word. It does too many things. It gets to be daunting, I think. Although, it works well in my work setting, but Slack is much simpler. It just has a channel that's the whole group of us that we can communicate on and share, and then it has the direct messaging, or DMs is what they call it, direct messaging channels, which is just between you and me. So whenever you're using Slack and you want to ask me a question one-on-one, you direct message me and I direct message you back. When you want to turn in an assignment, you turn it in by dragging and dropping it into Slack, and then it shows up on our direct message chain, and I grab it off there and put it in a folder for grading, and then I'll push it back out after it's graded. So in the end, there'll be 2 copies of it for each assignment on that DM channel, because it'll be the original raw and then the returned one. And because Slack is a pay for app, the free version, which I'm using, has a lot of features removed from it. Number one is it only has a 90-day window, so after 90 days things get erased, and I guess I'll go back to it. And so you signed in, Lantu, is that right? Yeah, she signed in, so I'd write back to her. My typing's not really great. The fingers on this hand are starting to work, but initially extremely painful and still at times very painful. I am right-handed though, so the fact that this hand was wiped out on me from the surgery has not been as bad as it could be. I'll explain that at some point. Why did I have the surgery? Because it was an elective surgery. So she writes back to me, and then you can just go over and join the channel. And if you scroll up on this, you can see as of December 23rd, 2024, that was the last communication I sent out, and none of that is visible because it gets erased over time. But my experience from last year was it works well enough. 90 days is a time window that I think is sufficient. Does it make sense? You pull stuff off of there, if they're documents or anything, you pull stuff off and you'll have them. You just won't be able to go back to stuff that you wrote. It could be good. If you wrote something you're embarrassed by, it goes away eventually. Nobody can see it. I could make it all visible, but I'd have to pay money, and I'm definitely not going to do that. The university would say you should be using Teams. I started using Slack during COVID, so that's what got me into it. But one good thing that it does is when you're on a direct messaging channel, I can just pick up the direct messaging channel, and I can go up here and we can do a huddle. And a huddle is voice, call, and screen share. And Teams, it's very much the way Teams works. So if that's something you want to do, of course, just like with Teams, you wouldn't expect me to be there at every moment of the day. And if you wanted to do a call to talk about anything, make an appointment effectively. But the nice thing about Slack for me is that I can put it on my phone. It's annoying to get slacked, is my terminology, like I just got slacked with another message. But it's convenient. If you've worked with Teams a lot, Microsoft Teams is really big and ugly to have on all your devices, I think. That's my view. Slack is fairly lightweight, and you can use it on the web, too, if you don't want to put the actual app on. I don't know. At those of you that have already responded back, did you just use the web version initially, or did you put the app on your phone or device?
I'm on my phone.
Okay. Okay, great, great. Okay, so back to where I was at. So there's a lot of info here in terms of getting into using the Jupyter Notebook in Python. That is, I've got a bunch of tutorials on that, basically just sets of examples that go. And I've got PDF renderings of most all the notebooks on here too, so you can see exactly what's in the notebook, what type of code examples and things are in there.
Do you get there from Slack?
No, everything, this is all on the UCCS website.
Oh.
Yeah, Slack is really just sort of a compartmental thing over here off to the side for communicating. The website is the main thing, and it's what's on the syllabus. And if you're taking the lab, the 4680 lab is on here too. And I work with the lab instructor on this. And I encourage you to take the lab if you're interested in the hands-on side of things. I personally find that hands-on gives people a lot more understanding, and some learners actually do much better if they have the hands-on part, because the plain theory stuff gets daunting at times. With that said, though, you will be doing some real-time DSP in the lecture, and I use Jupyter Notebooks to do that, and I'll explain that. So you'll be setting up a streaming means for doing real-time DSP right in a Jupyter Notebook. And the Jupyter Notebooks that I'm talking about run Python. Jupyter Notebook itself runs other languages, and Jupyter Notebook can run either in its own web app or it can run under VS Code. And how many of you use VS Code or have been using it? Okay, at least one. So you might like it in VS Code better. There's pros and cons to each. I've used both extensively in my last year working on this space radio at this company here in town called ARCA. And if you've heard of ARCA before, there's multiple divisions of ARCA. So the Colorado Springs division was Emergent Technologies, and the division I've been working for is in Bothell, Washington. The name of that division is Tethers. However, they shut the operation down there and moved all the lab stuff here to Colorado Springs. And our customer has been Blue Origin, which, does everybody know what who Blue Origin is? The Amazon space company. So I look at it as, it's been really fun work. I've been working on a project called Blue Moon, so it's a space radio for things going out to the moon and communicating. And I'm on the comm links for that. Spread spectrum radio. I can talk about these things. Generally, I work for companies where I have the clearance and I have all the knowledge of stuff I can't talk about, but this is fun because it's commercial space electronics. It's small. What does a space radio look like if you're not familiar with them? It's a small cube that's about 6 inches, well, 6 by 6, and then maybe about 3-4 inches tall. It's a very small little compact device. It has all the RF interfaces in it, and then it has the firmware and FPGA on there. So basically, I look at it as a device that has 3 sets of technologies. Number one, it has, well, power management, I suppose, too, but it has microcontroller or embedded system. It has FPGA, and then it has RF subsystems. So all of those play together, and I've been working on mostly receiver algorithms. You're not going to stay?
This is not my class.
Really?
I'm a sophomore.
Okay.
And I'm supposed to be in computer-based modeling in C. So,
okay. Okay. C is a good language because you need that for real-time systems. So, okay. Oh well. So it goes. You guys look like you're following what I'm saying. I mean, this is a really fun subject, and one of the things I believe in engineering, and I have all these tidbits, and I know I'm going to run out of time here, is that every day that you work as an engineer, if you're not having fun some part of the day, you're not in the right thing. you need to be somewhere else. So just be thinking about that if you're looking to find a job that you want to work in full time eventually. You got to have fun part of the time. Realize fun is not something that's guaranteed in life, and it can come and go, but some of it should be fun. And working on a team is also a lot of fun too. I mean, there's the camaraderie. I've been finding working on a virtual team through Teams, I've really only met a few people that work here in Colorado Springs, my manager and a couple of the other engineers, since I've been going to the lab the past week a lot to do testing. But everybody else are just faces that aren't even faces. I know what they look like because they all have their virtual face or whatever in Teams chats and sessions and everything. But I know a lot about people because you have a lot of discussions about more than just 100% work. So I know idiosyncrasies probably of everybody, just like you'll know my idiosyncrasies already and I'll learn yours, like, oh, that person comes, but maybe they walk in the door 5 minutes late. I mean, I'm not picking on you yet, but I mean, everybody in a Teams environment, everybody comes to work at their own time. So you're waiting for somebody to show up so we can start picking up from what we were doing the day before. So I think I've said enough about the website for right now in terms of what's out here. In terms of, I will say this, though, since I'm already onto this. Now, this you might find interesting. Last year, there were 4 whole people in the class, very much like we have right now. And don't take this too seriously, but this is the way it turned out at the end. This is the histograms from the whole semester. I had my ups and down feelings about the students from last year. It was 2 graduate students and 2 seniors that were in the class last year. We started with 6, and 2 people disappeared. 1 for reasons outside of the class. 2 not able to handle the material. So things like that happen, though. But in terms of getting set up with Python, this document is really good right here. This is also linked on the syllabus. If you should want to go with Play with Julia, then the second document is very good. There's things in the second document that pertain to production of PDF pages, but there's also other options there that I'm thinking about that I've already started to work on, but don't have it totally ready because I was thinking we were starting tomorrow. But this one, if you've never set up Python, and I'll show an example of launching that and everything here before we leave today, this gets you set up using Miniconda as your base for a Python, scientific Python environment. I'll just ask right now, how many have used Conda or set up a Python virtual environment just so you can have the tools you want in Python?
Sir, I set up a Jupyter notebook.
Okay.
For fun, so just see if I can do it.
Okay. It works.
It worked, but I need to play with it some more. I've been playing with C++ and I'm doing Python.
Yeah. Well, you can see that one semester I had a project that did some C++ development, had everybody put this on their systems to do part of one of the projects in C++. In the end, it was not something that made people very happy. They didn't like it a lot, so I developed a new project in Python, a software-defined radio kind of a project, and I'm going to be probably leaning towards refining that and having you to do that this year. Not for certain, but thinking about it. The first project will be more like the current project that's up there, and the projects are over here. Last year we had 2 project 2s, so it's this project option B that I'm probably going to lean towards, an FFT channelizer, which you don't have to know what that means, but it's pretty interesting project involving some real captures, signal captures. And the first one involves some real-time audio and algorithms running in the Jupyter Notebook. The Pluto notebooks and Julia is just hanging out there. I've been excited about it. I used it for one company till I was terminated from that company in March a year ago. I like it a lot. It's a lot faster. It's a little bit more challenging language to get into using. And Python is not a trivial zero input language either, although in the end it's a pretty easy language to learn the concepts of. So the language that you might want to consider that I wrote a package for, I already pushed it out here, is Maxima, which is an old computer algebra system that gets updated very regularly, actually. And I used it when I wrote the Signals and Systems for Dummies book. So somebody from Europe who bought the book early this year kind of was like, aren't you going to provide more Maxima support? And I took it as a challenge because I'm a tinkerer in my after hours besides playing music a lot. I wrote this package and I finally published it a few weeks back. So I'll show you about Maxima, but if you've used Mathematica ever before, it's very similar to Mathematica, but it's open source and probably not as glitzy as Mathematica became. It's just out there, and I did it for the community really because of the fact that people were asking me about it. And I'm curious, you know, when you retire or stop working so hard, what are you going to do with your time? And I spend my time doing a lot of different things, but I have enjoyed open source software. I've benefited from it a lot, and I feel like if you got an idea and you want to spend some time on it, you can go publish it on GitHub and nobody's going to stop you, and you can get some rapport going from people. I don't expect people young like you to want to go off and do that, but there are people like you that like to publish stuff in open source software. But it's kind of a hobby activity. My wife has always thought you're working all the time. I said, when I'm sitting at the computer, I'm not necessarily working like you might think I'm working when I'm putting in hours for a company. I'm messing around with stuff. So I think it's fair. Again, engineers are maybe different than people that don't do engineering. Okay, so I'm going to now switch gears here and go and talk a little bit about the class background and expectations. So this is lecture 1, which is on the website. Maybe I didn't show you where that link is. Formally, if you drop down, I have links elsewhere to it, but formally, if you drop into course materials, and you'll refer to this course materials a lot, this section down here. Course syllabus, which I gave you a paper copy of, is here. The intro lecture, or chapter 1, is what we're going to look at now, and then other lecture note chapters, and then some other supporting documents are linked down in here. And these things will change, be updated, whatever, like this last one. That'll obviously change for 2025. What I do is I will announce things on the website homepage section up in here, News For section, and then I will also put messages in the Slack channel just to let you know, hey, I've added something, go take a look at this. So you got multiple ways of hearing about it. So back over here, and I forgot to bring my water bottle, so that's maybe going to limit me. This is like the cover page that I made for the notes years ago, but this is an interesting systems sort of block diagram with some graphics that I will walk through here in a moment or two. What do I do on the first day, though, is I give you this quick introduction, what the class is about, talk about contemporary DSP, which to me is the technology of what makes it work and the key application areas, and then the perspective of this class from the DSP area in electrical and computer engineering, which, sad to say, is dead because my replacement has never been hired yet, and it'll be 3 years coming at the end of this semester. What's going on around here, I don't know. I find things kind of deplorable in a lot of ways. Your students, I shouldn't be saying that, but you started here, you don't know what's going to happen, but there's definitely been hard times going on here, I feel like, financially, mostly. Specifically what the course is about: software analysis and simulation tools, computer projects, the syllabus, which is a separate item, and then at the end, instructor policies. So I'm actually going to just jump down here to this just to make sure I can get through it because it goes along with the syllabus. We've already talked about a lot of this stuff, but at the top you can see if today was a due date for homework papers, I would expect, unless you were writing me on Slack some excuse or whatever, that you would have your papers pushed to me on Slack by noon on the due date. Reasonable? And I've also found that people will push a copy and they'll push it early. They'll think, I'm happy, and then I'll push some hints or something will be said in class, and somebody says, I didn't really want you to have that yet. I want to push it again. So, fine. The onus is on you to delete that old version, though, that's pushed on Slack, and then push a new one. Obviously, if you're on business travel or other activities keep you from attending, I just would like to know beforehand. If you're sick, got in a car accident, there's a traffic jam, yeah, if you can message me, that would be nice to know. I start with a grading scale that's just straight and then curve as needed. And if we were to study the histogram from last year, definitely I had curving in there. But that's pretty straight there. And although I don't use a course management system per se, where I put all the grades in and have it automatically give you a histogram, I do that and I push that up on the website. So you will see how things are unfolding, like how your competition is doing. Is that reasonable? I mean, the concept I know is how am I doing? You got a grade, you think it's bad, and then I show you what everybody else did, and hopefully that you can say, oh, okay, I understand. You might still be doing bad, or you might still be doing good, but at least you have a perspective, because I know where you're coming from. Screencasting, we're underway with already. Homework solutions, like I said, would get posted. We'll establish a password, and I'll talk about the password on the Slack channel. It'll be something very memorable, though, that you'll be able to easily enter in to get the solutions pages up. And when we have exams, old exams will get posted with solutions in advance. So you'll have at least 2 to look at. So now getting into this, what I look at for DSP is theory. I didn't have that in the intro page there. Theory, technology, and application. So theory, Modern DSP was the name of this class when I started back in 1984. That's how long I've been, that's when I started as a faculty member in 1984. I didn't teach the class initially, but somebody had put the course name on the books, and eventually another faculty member left, and I took the class over. So modern is very vague, right? You could always say modern of anything. But I think the idea is that it's supposed to be following contemporary ideas and how things go. So the theory started back in the 60s, and it grew out of, it became college teaching in the 60s and 70s, and then the technology started eventually maturing, and it left the world of simply military technology. You know, just think about history. Where does most great technology for national security and defense come about? Through research labs and stuff that never gets published. And then eventually there becomes something that becomes more commercial and more, you know, in our society. And this has definitely been an example of that. I think if we went way, way back in time, way before your time, there was a doll that Texas Instruments was part of. It was called Speak and Spell. I think it was a doll that talked. I mean, I don't remember the details of it. I had a younger sister, but I'm pretty sure she never had one of those, if they did exist then. But that was a commercial technology. It started showing up in telephone channel modems, which none of us use anymore either, but when you used to have to plug into your phone jack to get connected to the internet, it was part of that. And the programmability of the DSP was actually part of that too, because that was the first device I can remember where firmware would be available and could be delivered to you probably by the internet, and you could flash into that piece of technology new DSP algorithms. That was very cool. Now you're saying, oh, that's so old. I mean, but we didn't start that way. And the applications for it have been just growing by leaps and bounds, and I have a separate page on that. So the expected background for this class is that you've come through from UCCS 2610, which is Signals and Systems 1, mostly the discrete time part of it, and then 3205, which finishes off the discrete time with some filter design and other modeling things in that 3205. And that 3205 class, Signals and Systems 2, is got circuits theory in it too. We're not doing circuits theory. We may have simple interfaces at times that you might see in a model or an analogy. There might be a circuits model equivalent, like if you want to have an RC low-pass filter, what type of digital filter is that equivalent to? And I'll walk through that sometime or another. I think it's something that's really important to understand how that filter comes into being, and actually that type of filter is used in, you know, is being used in my project at work right now, and I call it a smoothing filter, and I call it a one-tap or first-order IIR filter, but you can write out equations, and you can say the RC time constant is equivalent to this coefficient in this one-tap filter. I think that's part of the history of this, and that particular filter is really popular, and I may drill into that more because I've had to drill into it more at work with fixed point integer arithmetic implementations, and that's something that is a harsh reality. Have you ever thought about writing code? If you've been involved with FPGA, what does FPGA like to do its math in? Integers, right? When you take the lab course, you get to use floating point numbers, and you have 32-bit floats available. When you take those floats away, then you have to be very careful about how you do things with the math. So I found a nice package over the last year called FXP for Python, which is obviously open source, and you can do modeling for integer algorithms and things. So where are we going to go from here? If you've already had basic DSP in 2 other undergraduate classes, this expands it. The math is more detailed. The attributes involved with the basic discrete time signals goes, you know, kind of ballistic. It blows way up into the types of things you see in real applications. And we also go down the pathway with random signals. We use probability and random variables background to go into random signals, which lets us model with noise and other types of waveforms. And one of the main things of the class is to teach you the foundations of discrete time signals and systems in the modern or expanded view of what you've already started in. So there's a lot of leaning on what you've already learned, which is good. What's a better way to have an engineering class? Starting from cold scratch, no previous background, or just, picking up and continuing a thread or two and introducing some new topics. So this is absolutely that. So you can lean on your previous background, and if there's things I think I want you to avoid, or maybe you got into a bad habit or something with the previous class, I will be pointing those things out to you, like partial fraction expansion. I'm 99.9% certain what was in the 2610 book, since I was involved with that, and that was the reason why I wrote the Signals and Systems for Dummies book, that is good. Georgia Tech was involved with that, and then the book that was originally used for 3205 had a thread back to Georgia Tech, and this book right here was written by a guy from MIT and a guy from Georgia Tech, so they're like founding fathers in the DSP textbooks for use in ECE programs. And originally, when I was in school, only graduate students took DSP because it wasn't developed enough. It wasn't considered to be commonplace. It was considered to be maybe too hard. I don't know. It's not a particularly easy topic, but I minored in electromagnetics. I took advanced electromagnetics, and the math in electromagnetics is different because it's Maxwell's equations, but it's still very tedious. This is not quite like that. Do any of you like Maxwell's equations in electromagnetics?
Only if I could plug them into a calculator.
Okay. I mean, it's fun. I mean, transmission line theory is important, and that is something that I rely on a lot. But this is, I don't know, it's got a really nice blend to it. If you like your computer, and if you like writing code, and if you like modeling and using your brain in a system setting of how do we look at signals, time domain, frequency domain, maybe the Z domain, so we have poles and zeros, everything is there to give you the right flavor to it. And you don't use all that stuff intimately in the practical development, but you have to touch on it enough that, in my role, working with my team, they're mostly FPGA implementers. And I always thought in the beginning, when I was teaching a long time ago, that if people would go to school and they would be in this class and then they would do FPGA and get really good at it, they could walk into a job and they could straddle both areas. They could be both the systems designer and the implementer. Well, as I found out back in 2023 when I left here and started working in industry and really being close with FPGA people, I found out, what do you think I found out?
Can't do it.
It hasn't changed. FPGA implementers will implement DSP things. You have to kind of push and prod and get them to make it work because they don't want to think about systems. They just want to think about registers and Verilog or VHDL. And modeling, how should it really work in the end? Well, they have ideas because they learn things over time, but it's still pretty much the same way. So I'm working with, I call them implementers because that's what they do. Like if you were a systems modeler and you said I want a circuit designer to design the circuit to implement my idea, that would be a different type of implementer, an analog circuit implementer. So some of you maybe have aspirations, and I'm not telling you don't try to do it. I think if you know something about what the other side is doing, you're always going to be better. And my first job, I ended up working with an implementer, but really we were working with an off-the-shelf modem design, and I used Vivado, which is the primary tool that Xilinx would use for developing, and I got into using Xilinx and its waveform viewer and all that stuff, and I could write test vectors in Python or Julia, push them in and run simulations in Vivado, and then the build could happen and the FPGA implementer would finish the build and then put it on in the device and I could be testing it. So I got exposure to that, and I got exposure to the embedded system side of it too, so I'm seeing that happening all over again, although I don't really want to be an expert in that. I want to stay on my task, and that's how I'm thinking of this class. So we'll be learning the new topics. That's what this course is about, seeing how they all fit together. We'll spend a lot of time with modeling and simulating. I think it's very valuable. I don't think in this point in time or the timeline of technology that we can ignore modeling and simulation. If you want to just fly by the seat of your pants and tell the implementer from a block diagram in a few words, this is exactly what I want, and you have never simulated it or evaluated things with some test vector inputs, you're in a bad way. You're going to be failing, and it's expensive to put an implementer on a task and say, no, I was wrong, it needs to be like this, this, and this. So simulation is very powerful, and another thing I became a strong believer in is that object-oriented programming. I realize C that you learn in ECE is very good, and it's very powerful, and you can make objects out of C, but officially going to C++ or Python is object-oriented, learning how to build objects. I will expose you to that some too. How many of you have already done that on your own? The object model concept of software? Okay. You said you were using C++. You don't have to use classes in C++, but Python makes it pretty easy. Python is actually really nice. And I'll try to explain that to you too. I'm not forcing it down your throat, but I just feel like if you don't start ingesting that, it'll put you at a disadvantage. So I skipped ahead. I already went through this. Our book is in here, and if I was to say this book was going to get replaced, I would say, based on my looking at it when I received it a couple of years ago, this one might become the front runner at some point in time, because the other authors are aging out. I mean, I'm old and they're much older than me, and they'll be, dying soon. And that's the reality of it, right? They're not to that point yet. I think Oppenheim is still at MIT, but something new has to come along. But I've taught out of this book for a long time. I used this one when I was a student also. So, okay, technology.
Speaking about the textbook.
Yeah, do you want to see it? I'll pass it around.
Not just that.
It could kill you, though, if it landed wrong on your body. It's very heavy.
I'm part of the TAPS program.
Okay.
Yeah, and so I was trying to look up ways to get the textbook or redeem it on TAPS. It says the only way I could find out is if you open up Canvas and you can enter there.
Okay, I know we went through this last year, and we resolved it. I did not have to go on to Canvas. I don't know what it was, though, because there's a paperback version of this that you can get for around $100, I think, or maybe it's less than $100. Do you want to be a point person and talk to me about it through Slack, about how it works? I mean, I can get into Canvas. I haven't been in it for years, but I know I have an account there. I don't know. And maybe give me a link on TAPS, too, because I've heard about it, but I don't remember how it works. What I'm going to do for this first assignment, though, which I did last year, I'll go up and scan the pages out of the book and I'll put those in Slack so you'll see what the problems are in the actual wording. And the course notes will be adequate. The book is better because it's got more stuff, but my notes were written from the book plus other stuff I've added over the years. So I'll be expecting to hear from you on Slack to help me move on that.
Yeah, I sent tabs some emails saying if there's alternate ways to.
Okay, that's good. I know I didn't have to do something specifically on Canvas, and people got it, and they talked amongst themselves because I started seeing it in class shortly thereafter. I got it. And I know it's a paperback version. Does anybody already have a paperback version? You have the hardcover one. But there is a paperback, which is much cheaper. You got yours used probably, right? Yeah, that's it right there.
Same like cover, but
yeah. And how much did that cost you?
This was like $20-30.
Okay.
I found it on, it's called abebooks.com.
Abe is the name of it, I think. But yeah.
Books, yeah.
Yeah, sure. That's the copy you want to get. That's the one you want to get. And if you want to sell yours back, this is better probably. I don't know. It's on better paper. But for me, I didn't bring my backpack because this arm thing, I'm just not wanting to mess myself up. It's heavy.
So that was like $7. That's not the right edition. But you have to like find the right edition of it. This one's edition 3. I think that's right. That one's literally $10.
So maybe that was the way we got around it last year.
The new one is $30. Used is $10. So yeah, they have a bunch of options.
Why don't one of you grab this as soon as we're done here and just see if the problem assignments match yours, or grab it right now. I'm pretty sure it works though, but I'll still scan it.
It had the same it's called like an ISBN number or something.
Yeah, ISBN. Yeah.
And it had the same one.
Yeah. I could tell a long story about that and why publishing books is not making money, but it has to do with certain countries of the world don't respect copyright, and then it blows the whole thing up. But my Dummies book sells for $20, and I don't make any money on it at all. So I didn't write it to make money, but at one time people could make a lot of money from writing books. So the technology, I think what I want to do is pick this up next time, and I want to go show you some things and how they work. I want to go back and talk about the cover. So let's go back and do that. We have 15 minutes left, and I want to have a little bit of time to pack up. I'm not moving really fast. I don't know, from a distance, does it look like I just have my hand wrapped, or can you tell there's a splint in here? This is not a lightweight thing. It's got mass to it. And I feel like I got to go easy. My wife thinks I'm pretty crazy for trying to do too much, but plus I'll tell you a little story about what I had done too. So just to give you an idea from Signals and Systems, though, what is going on here. Here we have a discrete time signal, triangles on the top. It's called a stem plot in MATLAB, and it's called a stem plot in Python. It's called a stem plot in Maxima, as I wrote my cutoff for that. So that signal is going into a system, and I'm representing the system inside the block there as saying the frequency response shows that it's having a notch at some frequency. That's this deep dip. From a distance, a mechanical analogy is that looks like the cross-section of a thumbtack. Does that sound believable? The thumbtack is point of it's right there, and the top of it's the head. And we'll study the mathematics of building this type of notch. So it's notching something, and in terms of the poles and zeros that correspond to that notch, we'll be learning or relearning how the z-plane, which is the dual of the s-plane in the continuous time domain, can look something like this. So we can put a pole on the unit circle, and that's where the frequency response is evaluated by cruising around on the unit circle, and then we put a a 0 out there and a pole just behind it, and to make it a real system, real impulse response, we have to have a conjugate symmetrical situation, pole and 0. I mean pole and a conjugate reciprocal pole and a conjugate reciprocal 0. By adjusting the location of that pole, we can tighten up how sharp the notch is. So we put the pole closer to the unit circle, and it will make it even sharper. Pull it back, it'll be broader, and it will look sloppier. So if we were listening to music that was being sent and we were removing a jamming signal, let's say, this would, we'd want to make the radius of that pole pretty close to 1, but what happens if we set it equal to 1? I'm just testing your memory. What happens if a pole goes on the unit circle in the z domain? It's analogous to a pole going on the j omega axis in the s-plane. Thinking back. You don't have to remember, but you'll eventually get refreshed. If a pole goes out there, we'll have an oscillation. And if it goes to the other side, we'll have an unbounded oscillation. It will explode. So we can let it get close, but if we're using fixed point arithmetic, let's say, we can't let the pole go to 0.999 because we'll have problems representing that in a fixed point integer math situation, but we can get it pretty close. So what is happening here, if you were to work backwards, you'd say I have a single sinusoid coming out. So if I have a sinusoid coming out with some transient, just because of going through the filter in the beginning, if the sinusoid is coming out, you can deduce what must be present up there. Because if the system is the notch, and the notch is going to block one signal predominantly, what must be coming in? 2 sinusoids, right? So one of them is annihilated by the notch, the other one comes through. I'm working on a problem at work, troubleshooting with the FPGA guy. We'll be back at it again later today, where it's like a black box. We can't do what's called a chip scope right now on the FPGA to see actually waveforms or signal samples, where we're stimulating it with different types of conditions, and we're trying to figure out what's not happening the way it's supposed to happen. And it's more sophisticated than this, but what I'm working on in that situation is, because space radio has to work on a space radio channel, platforms are moving, and when a platform is moving relative to another platform in space, what happens? I'm thinking of physics now. If a platform is stationary, the channel is fixed, no, there's just a fixed time delay, right? But if we're moving away or moving closer, what happens from physics? Yeah, but what's the phenomenon? When you're outside and you hear a siren on the street go by, you hear Doppler. Yeah, exactly. So Doppler, if it's coming closer, then the frequency goes up because the waves are pushed together apart. So our system has to be tested with Doppler, constant Doppler, and Doppler rate. So Doppler rate means it's not only moving closer or further apart, it's got an acceleration associated with it too. And then all the other derivatives are there to some extent, because the orbital mechanics, did I want to learn about orbital mechanics and do modeling with that? I've had to do that past over 10 years now, so I relearn your physics and you learn how orbital mechanics factors in, and there's a Python package for that too. So you can get what the radial looks like. So the radial vector will be a function of time, and then all the derivatives are there, so it's not just simply Doppler and Doppler rate, it'll be higher orders and other stuff, because orbital mechanics will say two objects are moving relative to each other in space, and you have more phenomena there. But we have simpler requirements. We have a Doppler and a Doppler rate requirement. So I have a channel simulator, which is an interesting topic. I won't get distracted on right now, but I worked for another company and worked on developing a time variable time delay, and that's in the Python package. So time delay is one thing, but making the time delay a function of time, that's another thing, and that has an application in music too. You can do something called the flanging effect, if you've ever heard of that. Does anybody ever listen to rock music or know what happened in the 60s? They had a bunch of special effects for guitar and voice, and that wasn't done with a digital delay line, but it was done with analog signal processing. So go back over to our website. I can't show this to you today, but I do have, under Julia, I was going to show this to you, and this computer's got issues. It's getting slower, or it's just older. I don't know. I couldn't get something to build properly. But if I go down here, I have this notch demo, and I have the PDF rendering. So in Julia, I was able to create the waveforms, and then I have this block diagram of what the model looks like. Let's see. It's right there. So I created a model of what you saw in that front cover. I put 2 notch filters in with programmable delays or programmable centers. I upsampled by a factor of 10. That's something we'll learn about, how we can change sampling rates up and down. And then I linearly interpolated that so I could have a smoother waveform to work with. And this is just the output after it's gone through its interpolator transient. We'll learn about interpolators. There's the mathematical model of the notch filter. And then I was able to put into the Jupyter or the Pluto notebook, I was able to put up some sliders. You can do this in Python too, where I could change the frequency of the sinusoid. The other second sinusoidal frequency was fixed in this model, I believe. And then I could set the 2 different notch frequencies, and I could change the pole radius. So this plot then, if it was running, it's interactive, and I can move it around. I can see the pole and zero plot move around. I can see the 2 notches move, and then I can see, I can annihilate one or both sinusoids. That's part of what a systems engineer does, though. I mean, we have to have, as a systems engineer, we have to have a vision. You have a concept explained to you by somebody, and you have a vision of how am I going to make that happen? How am I going to make it work? And then you start creating that design, and then you end up testing it in a software simulation tool. I have another rendition of that model actually over here, because I put something statically in this package. So the WX Maxima package that I wrote, I have an example IIR notch filter design for audio signal with tone jamming. So this has been a project used in this class where I give you a speech waveform or music, and then you hear some jamming tones on it, and it's very annoying to hear that jamming. So how do I do that? I have to figure out where the notch frequency is, and then I can tune the notch, and I'm going to make it very like a thumbtack. I will extract or excise out that notch, that jamming tone, and the music will sound almost natural. I'll maybe miss a few hertz of music content, but it won't be that noticeable. Does that sound cool? So here in this example, I wrote Maxima code and did similar modeling, and in this case, there's my speech that has got the jamming tone on it, and when I send it through the notch filter, there's the speech. This was me talking or something. I recorded it on Pi Audio, but then I used Maxima to process it. So I like audio. I'm an amateur musician. That's the reason why my hand got operated on. I play bass trombone in a jazz band. It's a pretty heavy instrument. I've been playing it for a long time. The bass, maybe 15 years. As a whole, ever since I was in 5th grade, I've been playing trombone. And I wore out my bone in my hand called the trapezium. I don't have any cartilage there anymore, so I've been lifting my horn, playing long gigs, and it just gets more and more painful, but music is fun, you enjoy it, so your body, and you endure pain. Has anybody not endured pain that had to be able to do something? I mean, we all push ourselves to the limit, right? So I decided, after talking to other musicians and reading about it, I would talk about having a trapeziumectomy done, and that's what I had done. And then there's a synthetic tendon that's connecting my thumb and this first finger inside. It's a synthetic tendon called a mini tightrope, which is a medical company play on words there. Tightrope, trapezium, strange humor, right? Doctors have a humorous, I guess, too, but that is now connected in here, and I'm eventually going to start being able to strengthen it. Supposedly, I'm an avid cyclist, too, so I'm kind of shut down on that right now, too, but I want to get back to being able to play music, and I decided it would be worth some pain and suffering for a while. I think everybody will have things like that in their lifetime, though, where you have to make a decision. Do I want to do something, or do I want to just endure it till the end of my life? So I decided to go for it. So what else can we talk about? We didn't get to the schedule. Whoops. What you guys can do, though, on Slack is you could draw on your schedule. I had it right here. My plan was to sketch out some ideas. I mean, one idea for me, obviously, is that would work for me, that would meet my objective, would be this. And now that I know that the lab is effectively right over here, that would really be identical to what I already had on Wednesday. That may not work for anybody. Thursday evenings in general aren't fun for me anymore because I did that all my career here. I missed my son's sporting events and everything because I was always teaching in the evening. A price I paid, that was part of my job, I knew it. It just went with it. So I was used to teaching sometimes up to 10 p.m. I would teach a double session or 2 back-to-back sessions on the same night, which was insane, but I did it one semester. But I do play jazz music. Once I can get this healed up enough, I will be rehearsing and playing gigs usually on Thursday. So that's why Thursday was definitely going to be out for me, because I can't instantly drive over to a performance, get set up and play, and be dressed accordingly. Can't do it. Just like sports, I mean, you wouldn't be able to go to the field, right? Can't do it that fast. So.
Would you be down for like Tuesday 4:45 to like 7:20?
That is one of my options. Yeah, that's one of the things I thought about. Tuesdays, I think the jazz band used to do Tuesdays, but we don't do gigs there anymore. That would work. So you're talking about this.
Yeah.
Okay. Another thing that would also work that I used to do would be just skewed slightly. I'm going to stop my video because this is, I want to get this wrapped up. Good morning. We're starting lecture number 2 on our first week, where we have an A and a B, or part A and part B. Starting next week, we will be 1 day a week, and the lecture video will be double length. So I'll probably take the video that I record today and merge it, even though I processed the other one, put it together before I push it onto YouTube. So what I want to do as we get started here today, I just want to show you that we are good to go. It's not quite what I was hoping for. This woman who's, hopefully I'll meet her afterwards, she ended up being the coordinator for the classroom, and Sarah Plett is the woman that works in the ECE office, And then there was the other guy that got involved with it. There was like 3 people working on it, and you know what? They were starting to go in opposite directions. One thought, oh, I want it on Wednesday, which I originally wanted weeks ago, and I said, we lost that opportunity because, you know, it never happened. You never knew about it, and they didn't do what I asked them. The other guy picked it up, and I said, let's get on the same page this time. Is everybody in agreement? This is what I want to do, and you should understand this is what you're supposed to be doing. It coalesced, and then she got back to me, and she offered me AEC 101 as the spot, and that's the Anschutz Engineering Center, which is the building right over here, the brand new building. And last time I got to teach in a brand new building in a new classroom was in the Health Sciences building down the hill when that opened up. It was a great place to be because the podium, I mean, everything technology-wise was about as good as it can be. And I imagine the furniture will be fairly nice, but maybe you've been there. I don't know what the furniture is like. I did walk through the building last spring, but I don't hang out here regularly, so that hopefully will finalize. I thought it was finalized because I had to say yes, yes, yes. You know, we do want to change it. All the students are in agreement, 100%. I'm in agreement. And then they said, oh, now we have to do all this, this, this. And I'm like, why? But so you guys have to be unenrolled and re-enrolled again. This is a new policy since last spring. I never experienced that before. I feel like you're getting tortured and I'm torturing the system because it shouldn't be that complex. But they've now added more duties for the administrators where they have to recycle everything. So this will be the 3rd time they've done it to create this class. They have to destroy the first one and create it again for the 3rd time. I don't know. I'm an engineer, so I think about I want to do real work. I don't want to do just administrative stuff. But you will get notified of that if you haven't already. Apparently, it still has to go through some more approval of something. So that's why this says, in the meantime, I've reserved the spot so nobody takes it. It's not 100% official, which I was hoping for, but we're pretty close. And so I did post the new assignment. However, it didn't take on the web app that I use. I don't know why that is. All the problems are the same. The due date is, and I will get that resolved when I finally get home after my occupational therapy appointment for my hand. The date that I posted, though, is September 9th. That's the tentative due date. So if you look on the calendar, here we are. We'll have this lecture next week. I'll be able to do more commenting and cover more material, and hopefully we'll be converging on that date. And I give specifics in the header that are a little bit different than the old assignment, namely because it's electronic turn-in. And like I said last week, I will give you till, well, I say on the sheet, I think, you have until noon of the due date day to actually push it to Slack to me. And if I decide to slide it, which I've done frequently in the past, I mean, for a due date based on how complex or questions, so on and so forth. In general, if I slide things down to a Friday to say it's due on Friday, then I let you say, okay, go to midnight. I wake up Saturday morning and I take inventory of what's been turned in and I say they made it. Or if they didn't make it, then I have to decide what I'm going to do if it's still not there. Question?
So if by next week they haven't destroyed this class and remade the one in the AEC classroom, are we going to be here at 8 a.m. or?
I don't think so. I don't think so at all. I just don't understand why they can't answer it. It's like it has to go through some more hoops, I guess. I don't know. I think it's a done deal because Sarah told me it was a done deal, and I had to confirm all of this stuff. I said, I want the classroom today. I'm releasing the classroom as of this morning so that anybody else that wants a classroom can grab this one. Yeah, I'm going to keep you in the loop, though, so stay tuned on the Modern DSP channel, is that working for everybody? Some of you didn't get in the channel right away on Slack, but I'm pedantic about it. I mean, you can always go look there, and just like last night, I said the assignment was posted, but it didn't make it for whatever reason.
Oh, you posted it under general last time.
Last night? Okay, that was probably because I was tired. I was I'm trying to take care of my hand, resting it so that it can heal. And if I posted it under the general, sorry about that, I will move it. But it didn't make it for whatever reason. It didn't make it onto the website. It's on my other computer, so I can't resolve that right now, but it'll be there. It's just problem 1, and problem 1 we'll walk through. It's convolving those 2 sequences is what you'll be doing on this problem. You'll first convolve it for n is equal to 5, and that will be a simple review of things you've already learned from 2610 and 3205. And then I'm going to have you do the convolution for an arbitrary value n, and that's going to up the ante, and it's going to be somewhat daunting. But I'm going to teach you some techniques using either Wolfram alpha for symbolic calculations involving sums, or WX maxima, which I listed as a help tool for this class. What it comes down to, though, when we get into this later today, when you have to convolve things, and we want to do it in closed form, just not doing it numerically in a closed form mathematical expression, we get involved with summations, and then we want to sum the series. Now, I don't know if you can think back to when you had to do that, if you did it in 2610 and if you did it in 3205, but thinking back more in time, if you had to do, with continuous time signals, if you had to do something, it generally, with convolution, involved an integral, an integration. So in discrete time signal processing, we don't have the integrals floating around, except occasionally we'll bump into those in the Fourier transform of a sequence, but in the time domain, we end up with sums, and the sum that shows up over and over again in this class, which we'll hopefully get to at the end of the class today, is the geometric series. Do you remember the geometric series from calculus? You would have done a unit on sequences and sums. Vaguely? Not vaguely? Okay. Okay. You're going to memorize this again. And this problem, because it doesn't have an exponential decay, it ends up being a different type of series that you'll be bumping into. And I have a page which I did add some more series sum terms too. So, and we're going to be relying on some of these other course materials. So one of them, we'll look at this one a little bit later, convolution sum extras. This is review and some examples and properties. This one right here, though, will be something that you'll print out, or if you want me to print it out, I'll print it out. It'll be on 3 sheets, and you'll have it for every exam you take, and you can refer to it when you're working homeworks too. But these are the types of sum formulas we'll be getting into, and we'll see we'll be bumping into them. We won't. I'm not intentionally driving in this direction. It's just, bam, you're there. It's like that's what engineering problem solving generally involves. You're confronted with something, and how are you gonna make your way through it? You're going to use, your robust math background. I say that because it is something that's way above the average person on the street, right? They don't do integrals. They don't sum series probably. However, I'll give examples here about how summing series and these types of calculations are actually intimately involved with another part of our life, and that's just a bank account, a checking account. What do our accounts do? They they bear interest, right? And that's a regression, or I mean a recursive process. You put money in, and then it gets a compounded interest, and that's actually related to the geometric series in here. So the arithmetic series are these first two. These are geometric, which we'll be seeing today. One's finite, the other's potentially infinite when we take it down here. And then a series like this, or like this one down here, is called arithmetic geometric. Do these things stick in your head at all from calculus?
Maybe.
Yeah?
We'll see.
Well, it's cool, though, because my son, when he was taking calculus at CSU, and then he switched majors, but he started in engineering, and the track experience kind of said, I'm going to do health and exercise science, which he finished in. But he continued all his calculus and physics with calculus, because my wife and I said, just get a math minor, and he did it, and he was successful. But he was famous for always saying, I can't remember any of this. I'm never going to be able to do anything with it. But what I found through my entire career is you learn something, it maybe sits dormant for a very, very long time, and then you're on a project at work or something, and something comes up, and you say, there's something in there that I've seen before, or I remember something in some course, and you might raise your hand and say, can I have that to work on? And you drill into it and you say, wow, I'm cashing in on something from way, way back, and now it's fresh in your head again. So I mean, I use calculus a lot still, and I use complex variables and other things in what I'm doing on this team. The FPGA developers, I don't think ever think about calculus, but I do, because it just factors into some of the orbital mechanics, or I was mentioning to you how things in motion, I mean, I have to worry about a first derivative or second derivative, and how that, when platforms are moving in space, that type of thing. And it's actually, I think it's rewarding to have that. You didn't go to school for naught. You went to get a background to allow you to solve problems. Okay, so back over here, we'll be talking about this eventually, but meanwhile we have to get back and wrap up some of the things I did not finish over here. If this will link, and I've got it in the opposite mode. Okay. I said I would show this to you. Generally, when I was a regular full-time faculty here, I would say, yeah, here you are. You're in Modern DSP. Where did you have to come from? You had to come from signals and systems. You had to come from problem stats to want to do this or be able to do it. And then where can you go from there? Well, you could go to real-time DSP, which doesn't get offered right now since there's nobody like me here. But if you walk over to the signal processing lab up there, it does have real-time DSP in it. It's sort of a miniature version of what the one semester class had in it. So if you were to take 4680, you would have it. Comm systems is on here. Other classes that follow, like Modern DSP, feeds into statistical signal processing, which hopefully a new faculty member will want to teach that. I haven't pushed it back out onto the website, but I probably will try to get to that since it's all out there. Why would I do that? It's because I want to be able to still have this website, which I started recreating because the university took the old one away, available so that hopefully this new faculty member who I've been imagining for 2 years now will show up and they'll say, what did you teach here in the past? And I'll be the old guy that can come in and talk to him and say, hey, I've got all these materials. These are the things we did in the past. Ideas for what you might want to do yourself or extend from that. So these are other classes, though, we used to offer. And I know the most requested class is Comm Systems 2. Some of you might have taken Comm 1 last spring already. They're both really good. To me, the Modern DSP is the implementation means to understand how modern comm systems are created, and the foundations of that is here, and then digital communications is in COM2, and more mixing in orbital mechanics and other things that go on with satellite communications is over here. Then other things related, information theory and coding, wireless and mobile communications. One of my specialty areas has been phase lock loops and synchronization. If you take COM1, you get introduced to phase lock loops. Did anybody take it already? Okay, you remember phase lock loops? It seems kind of esoteric, but every digital comm system has a phase lock loop in it, has many of them in it, and that's the big thing in what I've been working on for ARCA and Blue Moon project is I'm doing a spread spectrum receiver front end, or a D-spreader as it's called. It's one of the optional final projects for this class actually, and that's a tracking mechanism. It involves code tracking. So you have to track your local code with your received signals spreading code. GPS is an example where a spreading code is used. That's how your cell phone or GPS device can receive satellite signals from like 3 or more satellites. They all have a different spreading code. You synchronize all of those individually, and then you can extract something called the pseudo range. And from the pseudo range, you can compute position. We used to have one of the generations of cellular use spread spectrum as well, something called code division multiple access, when more than one user can be on the same radio frequency, but they're separated by different spreading codes. There's different multiple access schemes, but that's stuff that gets talked about in comm systems too. Does that sound interesting? I mean, if you go to work here in town for an aerospace company, these are all things that they're working on, and they've been working on. It's not a new thing. It's legacy with additions. Cellular telephony is generation 5, and then on into 6. More and more and more and more stuff. Generation 5, for example, offers the ability to have multi-element arrays. So if you look up the hillside behind us at the towers up there, that's already up there, the ability to have several elements to form beams, spatial signal processing, where you're going to form a beam. So I'm right here. My cell phone doesn't have a big array antenna on it, but they can still steer a beam at me and give me more signal without it interfering with other people that are neighboring. I mean, not in a pinpoint, but they can direct more signal power just at me if I'm requesting a higher data rate service, let's say. Probably haven't thought about that in the past. So the other thing that I'll move down to next, what is this course about? It's mostly the one-dimensional signal processing, and analytical skills is my primary importance. And we get that through working homework problems. If it's symbolic problem solving, because that helps us sum a series, that's what this first homework problem is going to drill into a little bit. Specialized applications, in my mind, is secondary, but I do talk about that a lot. I will talk about, when we get into multi-rate sampling, how a software-defined radio front end works and how multi-rate digital signal processing works. And multi-rate just means that we might sample at 100 megahertz in the front end of the radio, and then we end up subsampling that. We end up actually undersampling. And you're going to say, I thought Nyquist sampling theory that you learn about first in 2610, you always have to sample at greater than what?
2 times the fundamental.
Or highest frequency, right? You remember that?
Yeah.
You can undersample, though, with a bandpass signal, and I'll demonstrate that with a nice little graphics application I wrote years ago. You can create spectral images, and if it's band limited, then they can fold together and you can end up undersampling. And important because sampling, having a clock crank an A to D converter at a really high speed rate and process that high speed rate all the way through our radio front end is very inefficient. You know, we want our batteries to last a long time, so multi-rate processing adds a lot of efficiency, less operations per second is kind of what happens in there. So I already said this last time, but just up here in bullet form, it does parallel, what we're covering does parallel a lot from 2610 and the additional topics from 3205. And if you didn't go to UCCS for your undergraduate, I don't remember, did you go here? But you had similar courses probably in your degree, right? So it still plays together, but we're going to push the math and sort of the complexity and then the new topics. Develop models for A to D and D to A. Multi-rate processing is a really big thing to be brought into here because all systems do multi-rate processing these days. And a good example of where this first started, for me at least, and because you guys are too young to remember when the compact disc came into being, right? When you were born, the compact disc existed. So imagine not having a CD or streaming media for that matter. What did we have before that? We had analog recordings, we tuned in radio stations and TV stations, but when the compact disc was first introduced, that brought digital signal processing to consumer audio. And when they first developed that, they sampled at 44.1 kilosamples per second. And then they later developed technologies, and we'll be talking about that later in the class in Chapter 4, that would do multi-rate processing to, again, make things more efficient and improve the fidelity of everything. So they ended up with 4x oversampling, and then the invention of the sigma delta A to D converter brought it to highly oversampled systems. And does anybody ever heard of a sigma delta converter? They're pervasive. They're in all of our electronics. I mean, this headset I'm wearing most certainly has a sigma delta in it, just because you can get away with 1 bit per sample, and that seems impossible, right? You'd think to have fidelity in an analog waveform, you should have to end up with more than 1 bit per sample. Well, you do, but then you can reduce it down to the Nyquist rate, and that's what the sigma delta brings into play. We'll also get into discrete time random signals, and this is done to allow us to consider quantization effects. Remember I was mentioning last time that the work I've been doing with the Blue Moon project involves radio stuff and baseband signal processing, and the FPGA, which prefers integer arithmetic. So that's where quantization comes in. But statistical signal processing, which is a follow-on, and it shows up in COM Systems 2, we have noise present, and that's how we model noise. And I'll have you use noise in simulation models for sure. And you're saying what kind of noise, right? You took probability and random variables, so what types of noise are there? There's uniformly distributed noise, there's Gaussian distributed noise, which models physical behavior in electronics, and there's other types of, and then there's other ways of looking at noise. Is it wideband, narrowband? Is it pulsed? Those things won't show up in this class, but noise is present physically, but noise jamming is something an enemy might do to thwart the ability to communicate. If they can direct high-powered noise in a narrow band, that might just be the perfect thing to wipe out your radio system. So we've designed systems for military applications that take that into account. So I've mentioned tools before. I'm definitely favoring Python.
So why do you favor Python over like MATLAB and Julia and XMath?
Because I've got one ear blocked. I'm not.
Why do you like Python over MATLAB and all the other ones?
Okay. I actually like all of them, but Python, because I invested a lot of time in building a package for this class, and it's out there. It's been out there since 2017, but it's open source is the main reason. MATLAB is very expensive. For students, it's not that expensive, and for many, many years, I used it. I started using it back in 1986 when it first came out over C and C++, by the way. Great visualization with the graphics. And then I realized I was brainwashing everybody into a product that's very, very expensive for industry to buy. Is that necessarily bad? Not necessarily, but you know, we're taxpayers, government contractors might buy lots of license seats, and the company's making a lot of money, and that's not necessarily a bad thing either, but the open source community came along and developed other languages since then, and Python came along in back around 2000. Python was already in existence, but the scientific part of Python was not developed until much later. Julia came 10 years after that from MIT. MATLAB, you know, grew out of some other things much, much earlier. Mathematica and and Maxima, both of those are symbolic tools. They have common roots also to each other. What I like about Python, though, is I think it's one of the most popular programming languages, and engineers that know Python or have familiarity with it is a big advantage. On my team, everybody's using it, whether they're an FPGA developer for modeling and simulation or embedded systems type. But some people don't use Python to the same level. We're using the scientific side of it, and it's been tuned pretty well. It's not as fast as Julia, so that's why I switched over to Julia for a while. But overall, it's really balanced. In over the past 10 years, when I brought it into this class, everybody accepted it, learning it, and more recently, people have like, I want to learn that language better. So, and students have given me feedback that my summer job or internship job, I got to use a lot of Python, and I'm glad you made us use it. Some companies still have their MATLAB licenses, and that's what they'll want you to use. That's not going to go away. It's kind of it depends. Where I'm working now, they don't buy people MATLAB licenses unless they're justified. And I don't know about you, but if you have to check out a license just to do some simulation modeling, which is what some companies would do, that's a pain. It's better to just have it all available on your machine. So, and we can do that. So we have Scikit DSP-Com, and that's the package that I developed as a result of writing my Signals and Systems for Dummies book. Extended it a lot. And then most recently, 2 years ago, I started developing a Julia package. I haven't released it. I have found nobody that's really super excited when I was teaching this class the last 3 times that really wanted to learn Julia. I still like it, but I understand. What do I see at places I've worked? I see Python and some MATLAB. So I don't want to force you off a pathway that's way out in the weeds somewhere. Maxima, which is similar to Mathematica, is not something I see either. But in academia, where we maybe care about some symbolic solutions or want to be aware of alternatives, we have things like Maxima, Mathematica. I'll show you today how we could actually use Wolfram Alpha, which is Mathematica on the web. I think, I didn't ask this yet, but how many have you had used Wolfram Alpha over your lifetime at least once? Okay, I'll show it to you on the web. It's very friendly. I think they say they have it AI enhanced somehow or another, so what you type in to describe the problem can be more vague than it was at one time because of a learning model. It'll interpret, oh, I know what he or she's trying to say, and I'll show you that. I actually have got it running right now on this machine. Going all the way back to C and C++, there are some people that just do that. When I first left here, my first set of work that I did for a company called Augustus Aerospace was all in C++. I prototyped everything in Python or in Julia, and then I had to develop the final code in C++, which ended up becoming part of the delivery for what's on a satellite orbiting right now. So I got pretty good at using C++ again, writing classes, making it object-oriented. And did I ever learn that in school? No. Did I ever learn C in school? No, because they didn't have us do that. In my era, it was Fortran, just plain old Fortran, which you've probably heard of it. It's very powerful. There's a few areas within engineering that still use Fortran, believe it or not. I think chemical engineers have still liked using it because they have libraries available. Python, for example, deep inside NumPy and SciPy, there's some Fortran that's compiled into the back end of the Python language. It has to do with history and legacy type stuff. When we go over to real-time DSP, C and C++ are very popular. MicroPython is available for microcontrollers. You may have heard that. You may bump into that in Capstone Design. And now people are looking at using Rust. Has anybody ever heard of that language? That's a newer one too. For hardware description languages, Verilog and VHDL are probably the mainstay. On my projects I'm working on at work, I think they're mostly running in VHDL, but I'm going to guess somebody uses Verilog because those languages can be intermingled in a project. And if you take the HDL coding language here, I think you learn strictly Verilog. That was true last time I checked, but they're similar. In terms of hardware in the DSP lab, we've been using Cortex M4, wanted to switch to M7, have a board that runs M7, but more recently, as in over a month ago, I got interested in another development platform around an ARM processor for sure, but it's an interface, and so I funded through crowdsource the Bella Gem, which, that sounds really weird to me. Why would you do that? Well, I'm thinking about what we might do in the future. So for audio, if you're an audio person, which I am besides radios because I play music, I'm wanting to develop something to keep me from destroying my hearing in the jazz band I play in. It's very, very loud. I have to wear earplugs. I would like to have something more of an in-ear device, or IEM as they call it, in-ear monitor, where I can mix in the proper mix. And this board here, there's two variations on it, a 10 input or a 2 input. I'm seriously, well, I paid for two of them. I funded two of them for about $100. And then it runs on top of a board called the Beagle. Let's see, get down in here. It has an IDE. It's running embedded Linux. So the board that sits underneath it is an ARM processor. And the board that sits underneath it, trying to get down here to the bottom of it, way down here. It's the Beagle, let's see, Beagle Bone was the original board. These names will sound strange to you, but people that are engineers and companies that develop these things, it's now called the Pocket Beagle. It used to be called Beagle Bone, and then it became Beagle Bone Black. Now it's called the Pocket Beagle. Everybody's heard of Arduino, right? This is just another similar device to an Arduino, but this is more of an embedded processor, a little bit more like a Raspberry Pi, because that's what it runs, is an ARM core device. It runs a Linux operating system. So this Pocket Beagle does that, and then the audio that sits on top of it uses embedded Linux, real-time Linux. So timing constraints can be met for real-time processing. So you can follow this link off of this page. I won't get the board until November, so I won't know how I'm going to like it. But to me, what's cool about it is, and this is an engineering dilemma that we're all into. Just to do this class, I'm asking you to put Python on the packages I want you to have on and run this stuff. It takes effort to do that. You have to keep it up to date, and I'll talk about how you can keep your installations up to date. To do embedded work or to do FPGA, you have to have your tools on and you have to install them and maintain them. So what's nice about this Bella Gem from my point of view is that I will get a flash drive that goes into the Beagle board, and it will boot up into that Linux, and it will boot up all the tools. They'll already be there, and I connect to it through a web browser. So I control everything on a PC or a MacBook, whatever, and I won't have to worry about maintaining all the drivers because they'll probably be just flashing a new OS and build system for my Beagle board, then with the audio board on top of it. That's compelling to me, just like anything, maintaining things, it's compelling if you have an easier solution where a core of people that are really smart maintain that for you, and you don't have to weed through all of the Google, et cetera, et cetera. Admittedly, now our browsers all have the AI stuff when we do a search where it tries to find the right set of helps, but it's very, very nice, but it's still not perfect. Have you ever spent more than an hour trying to search and find something? Just because it's like, I can't figure out how to make this work, it's broken. Right? In work, you spend a lot of time doing that too. It hasn't gone away, or it's not going to go away. So Python is got a lot of nice capabilities, and when we install everything properly, package-wise, so we'll spend a little bit of time looking at that. Today, not very much, but one of the things I like about Python, though, is there's a package hierarchy. So I based my package, scikit-dsp-com, on top of SciPy and NumPy in particular. And NumPy makes Python more like the capabilities that MATLAB was designed to have. So Python is more of a Swiss Army knife type language. It can do all kinds of different things, but when you put on the stack of packages, which when I first got involved, it was called the SciPy stack. You install NumPy, SciPy, and then matplotlib. Those three together, the matplotlib gives you the graphics, the NumPy gives you the core vectorization for doing signal processing, and SciPy gives you specialty areas within it. And then there's a lot of other packages you can get involved with depending upon what you're doing. There's actually SymPy, for example, which brings symbolic computing to Python, but I find the interface to that is tedious to learn. Everything has a price to pay, as you already know. From life in general, but anything with technology. One of the things I like about Python, though, is there's a package developed at MIT called PyAudio, and then I wrote a package on top of that called PyAudio Helper, so we can use that to do this stuff we'll do in Project 1, do real-time DSP right in the Jupyter Notebook. And Jupyter Lab that you'll be installing or have installed already is another package that brings a nice GUI interface through a web browser to do your coding and documenting. So that came along since I've been in the community, which has been over 10 years now. I think that pretty much covers that. I was going to look at the syllabus, so I'm still going to look at the syllabus. I'm going to mostly home in on things I haven't talked about on here. Okay, so this area right in here. Now the pen's working. What made it work better than early? This is the contract, what I call the contract area of the syllabus. It talks about how you're evaluated for the class. So I must talk about this. I'm saying that with a smile, but for you, you're interested in it, right? And rightly so, you should be very interested. Homework assignments, which will have embedded some numerical computing and symbolic computing, 25% of your grade. I know that this book has been around for a long time. I know you can go searching for all kinds of things out there on the internet. I encourage you to not do that because, you know, just copying things from stuff you find out there is bad form. It's not really acceptable. And if I detect that sort of thing going on, I'm probably going to be bringing it up with you. If you got questions, bring them to me. I will answer your questions, and the hints pages I give you are actually designed to make you just say, hey, I can figure this out. I've got some hints. I know directions to go into. So just trying to find the solutions manual out there is not appropriate. You're seniors or graduate students, so I'm giving you 25% of your grade based on the work that you do to learn how to solve problems. So don't mess that up. Final computer project will be 20%, up to 20%, or 15%. There's a grade option because with a final exam, which is number 4 there, I make the exam worth either 25% or 30%, and it toggles with the final computer project. And what I do is on my spreadsheet, I calculate your grade both ways, and I give you the best of those two. Does that make sense? Project 1, and there are 2 computer projects, is the more tedious of the 2. Project 2, sort of the applications project, will be much easier. I'll lay things out really nicely, and it does come with a due date of finals week, but it's not nearly as complicated as Project 1. So I'm going to make sure we get started on Project 1 in September, and you can start grinding your way along with that. And of course, that will involve a lot of Python coding and just running things and using Python objects, doing the real-time DSP. But you're getting started on that right now by getting Python on your systems and getting the packages I'm asking for. The hour exams is the third element in there. There's 2 of them, and the first one will be in class. It'll probably be in late September, early October. I don't remember the exact dates. I'd have to look at the old exams. It'll be in class, worth 15%. You'll have this formula sheet that I showed you already today. That'll be something you'll be allowed to have in the exam, and then you'll have 1 double-sided sheet of your own notes that you can bring in. And you're going to have a scientific calculator. You can't have cell phone, tablet, blah, 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 you know, the normal stuff that you've seen here on campus. The second exam, though, has traditionally been a take-home exam. And I generally do that starting the week before Thanksgiving, so that you would get the exam maybe on as early as Tuesday of that week, since we're going to be meeting on Tuesdays. And then I have it due like on the following Tuesday. It used to be campus would have classes on Thanksgiving week. You guys are young enough, or old enough, I mean, to have had that happen, right? And I think last year was the first time we took the whole week off. Is that right? That's how I remember it.
I think so. I don't really remember.
Yeah. See, it's hard to remember everything, but nobody really wanted to come to class on Monday and Tuesday of Thanksgiving week, so they decided to give you that whole week off. And for us, now that we're on Tuesday, we wouldn't have class that week, even if we were, well, we would have had class, but I don't care. I have it worked because of the fact that it'll just be a take-home that'll be due, and we'll be communicating on it as need be. So I'm not trying to spoil your Thanksgiving time with your family, but I will have it due on Tuesday so you can be done with it and, you know, go wherever you need to go to be with your family, if that's what you end up doing. I'm not really going to talk about the topics because this is the book. So we're not covering everything in the book, but we are drilling into a lot of topics fairly nicely in detail. So I want to get started in the signals and systems part. It looks like I'm going to spend maybe 10 minutes on this, and then I'll spend a few minutes looking at tools and talking a little bit about that special problem, which you're going to want to get started on, or at least start looking at it. I'm going to try to go quickly here. I liked all the detail. I was reading another DSP book on Tuesday night, and I said, wow, this new book has got so much detail. How would you cover this in class? The author of that put lots of info in there. So one-dimensional signal is what we're focusing on, but a one-dimensional signal means it's a function of time or discrete time. So we can still have other variables independent of the time axis, like the amplitude, the phase, and the frequency, right? Those are things to think about with a sinusoid. If it was a pulse train, it might be the width of the pulse. And did it have some other periodic features embedded in it? Just so you know, 2D would be images, and 3D would be spatial scenes and things of that sort. All possible, but we're not going to focus on that in this class. So image processing traditionally has been a course unto itself, which computer science offered it at one point. We offered it here at least once over my many years of being here. But ideas transfer. Spatial signal processing also involves 3 variables. So as I was driving here, I was looking at a light pole, and I saw a small telemetry antenna on a light pole pointing somewhere, and I immediately thought, you know, it's probably a Yagi antenna, which the antenna looks like this, and it's got elements spaced along it like that. Has anybody ever seen an antenna that looks like that? What do you think's going on there? If you've had antennas from Dr. Song, you maybe already know, but we can think of each one of these as being a dipole antenna, or for digital signal processing, this would be like a single sensor, and it's spaced maybe a quarter of a wavelength apart or less than a quarter wavelength. And in terms of signal processing, we'll be able to view this as an FIR filter and how it has a frequency response that will be tapered. But rather than being an electrical frequency of like hertz, it will be a spatial frequency, which refers to the angle of arrival at the front of that antenna. So it can give it a beam shape where it's a lot of gain in one direction along the bore side of that antenna, and then it has side lobes off center from it. We, I'm saying, as signal processors, can have this view that sort of transcends even dumping into electromagnetics a lot, because we can abstract it. So, do you know that? Does the concept of abstraction appeal to you in general for engineering? Or maybe do you think it is pretty essential?
For the system that we build, I think it's pretty essential.
Yeah, I totally agree. If we had to learn how to build a resistor from scratch and be an expert at it, we'd be really burned out at this point in our career, right? Mm-hmm. You learn to accept a lumped element or a computer program with arrays and stuff. We have to abstract, so I like it myself. And object-oriented programming tries to do that for you by building an abstraction model where you have little software components that have properties that somebody carefully designed, but maybe you bought the library from somebody, so you can just use it rather than develop it. Our Python packages do a lot of that for us already. So terminology, we have inputs and outputs in continuous time systems. In the discrete time domain, we have inputs and outputs. In the digital system, we have inputs and outputs. Really, the only difference is when we talk about a digital system, we end up talking about the fact that in a digital signal, because it's on a computer or computing device, it's going to have amplitude values that are quantized. And that just says we have finite word length representation. And when you took C programming, you learned about the different data types in C, right? You had a float, a double, and now they might be abstracted to be a float 32 or a float 64 in a more modern header libraries. And then we have int 32, uint 32, remember that stuff? We deal with all that stuff here. And Python actually supports all of those types. It's built on top of C, so or C++, so it actually inherits all that stuff. I'm tempted to go down and look at something, but I'm not going to do it, but I'll encourage you to do it, though. I'll just jump over here for a second and just look at the website again. I did put this up, or put a link to it yesterday. So the link that was put in here was Python Basics. So I was asked about this after class. Did you end up looking at it some? Okay, look at it because it talks to you about setting up in more detail and using the tools once they are set up. And this goes over what NumPy offers in terms of data types and so on as well. It was developed in a Jupyter notebook, and that's right here. But the Python Basics is, it was written in the notebook, and then I exported the notebook as a markdown file, and then graphics are embedded in here. And different things about, like running Jupyter Lab here is demonstrated, where I launched it from the terminal in Windows by typing Jupyter Lab.
Is there an alternative way of running Jupyter Notebook besides trying to open up in PowerShell?
No. Well, actually, somebody created a package where you can install it on your device as an application. Yeah. And I looked at it the last year or so, and I found it to be I didn't like it. I just like running it in the web browser, and I do that at work all the time, or I run it in VS Code. But when you say Jupyter Notebook, it is called a notebook, but originally Notebook was the application that you ran, but nowadays we run Lab. So don't start down this pathway of running the notebook, which I think is still supported, but it's kind of inferior to the Lab. The Lab has this nicer GUI where you have the sidebar that can do different things, and then you have the tabs inside of it. I thought about that Tuesday. I said, I don't want you to get hooked into that because it works, but they're trying to deprecate it. And do you know what deprecation means in software? Deprecation is a term that's probably used in a lot of other things in life, but I know it best in software. Deprecation means we're going to eliminate this. It's absolutely going to go away. Like Windows 10 is officially deprecated by Microsoft starting next month or the month after. So the campus has said you can't have Windows 10 on any machines anymore on campus for security reasons because Microsoft's not going to maintain it. Does it mean you can't use it anymore? No. As a matter of fact, where I'm working right now, they've talked about needing to keep some Windows 10 machines running to run some software that they need for FPGA development in a really old environment. And they can't put those, eventually those computers won't be able to be safe on the network, so it just poses challenges. So I live through deprecation, and we'll see that in how I run it, but how I run Python, but there's alternatives to that. So deprecation is a nice way of saying, hey, you're okay right now, but be on guard. We're going to pull the rug out from underneath you at some point, and it's not going to be there anymore. So a sequence generally has the square brackets on it. That's what our book uses. When we talk about sampling an analog signal, we'll usually put a subscript A and mean analog, and we'll be sampling at some sample spacing, capital T. These are all things you've seen since 2610. We like to use the stem plot for plotting those sequences to really get embedded in our head that we have values here, next integer, which would be a time sample actually in an analog waveform. So we have just discrete values. We have no values in between. When we have to plot a lot of points, it's better off to just use plot in Python, let's say, so the dots get connected. But you always have to understand that there's no value between those points. It's just too many of those stems on one plot make it take a long time to plot, and it's just a blur of black lines or something. But the stem is really good in the beginning to get that flavor, and homework problem number 1, which I'll get resolved here later, does ask you to create some stem plots. You also do that in the last homework problem. So we have sequences, operations, like shifting a sequence. We have special, I'm going fast now because I want to get on to some little tool stuff. We have special sequences like the unit sample or impulse, very beautiful in discrete time. Remember the delta function in continuous time. What don't you like about the delta function? Give me your individual opinion, maybe. Is there something you don't like about it?
Remember the map.
Yeah, well, trying to envision a function that has 0 width but has area 1. So that's a little bit mind-boggling, right? This is beautiful because I wanted to have height 1. Effectively, its area is 1 because it really has no width to it. But in the discrete time domain, we can do that on the computer. We can model it that way. We don't have to worry about this kind of somewhat nebulous delta. We will have delta functions in the class, though, in the continuous variable sense. I'm not taking the time to go through this, talk about some systems, so I just want to get into what problem 1 is based on, if this thing will cooperate with me. We'll look at sinusoidal sequences, which are different than sinusoidal continuous time signals. We'll then get into systems where we have an input and an output. So if we have a system that's linear and time invariant, then we have a property, the system, that says that linearity holds. We can use superposition in forming the output from the many inputs, and time invariance means the system properties don't change with time. And once we have both of those conditions met, then we get into the domain of linear time invariant systems, and we get this wonderful result that says we can form a convolution sum to get the output of a system from its input and its impulse response. So a fundamental example here in the notes, which problem 1 in the homework is patterned after, is convolving a pulse with an exponential. So we have those two waveforms, in this case an exponential decay. I'm getting emails, I guess, from my web app. Flip the pulse around and slide it across. You remember doing this before? So this is worked in intimate detail right here in the notes. The homework problem that you have is this. It's, rather than being an exponential decay, it's a triangular shape, so it's just a linear decay. It drops from this is supposed to be n. Didn't get that drawn in here. Drops from n down to 0 at time index n. So you're going to be focusing on doing this convolution, and what you'll do in this convolution is you will follow the pattern here where we overlap and then we develop different intervals for the solution. We'll be able to say that when n is less than 0, there's no overlap, so there's no output. When n is greater than 0, but this is still not fully to the right of 0, we'll have another condition that's called partial overlap for this condition. And then in order to get the output, we have to be able to sum from 0 to n the product of the two signals, and we get this. That is a finite geometric series, and in the homework problem number 1, it's going to be an arithmetic series, so a little bit different, but still a series that is summable. So I'm going to kind of stop looking at this level of detail right now, but in the homework problem number 1, the picture is going to look just like this, except that rather than having this exponential that goes out to infinity, it's just going to come out with a straight line and it's going to stop at n. Or if I set n equal to 5, which is what the first part of the problem does, it'll just be finite. But you'll have an interval like this where you're going to be summing, and you'll be summing, actually, in the homework problem, you'll be summing n minus k. That's because that's the triangle falling off. It starts out at n, and then as it moves along as a function of k, it's eventually, when k gets to n, it will be at 0. Does that make sense? It's just a line. So you'll be doing that sum, and so you'll have to do that. And in tools-wise, we're going to run out of time. I'm disappointed in myself because I'm not managing the time well enough, but here's Wolfram Alpha, which I just brought up in the web browser. So let's suppose I want to, this is the language that you can use. This is a good example. This will be captured on the video, but this is what Wolfram Alpha now supports, a very simple, in-your-face language. I mean, I say in-your-face, it's like I'm just going to tell it what I want to do in words and keep it, the KISS principle, keep it simple, stupid. Is everybody like that? Okay. So let's just do what we just did. We want to sum k, that it's not n minus k, but I'll start out with k. I want to sum it from k is equal to 0 to n, just a partial sum like I was showing you in the notes there. And in this case it won't matter, but I can make an assumption over here. I can control things. I can assume that n is less than big N, assuming N is less than big N. Because if I go beyond N, I run out of triangle. It goes to 0 at that point. So you can make things like assumptions. So put that in here, and it first gives you the interpretation. It tells me, I think this is what you were telling me in mathematical form. You like that? I think it's really cool. It's like, did you get this right or not? Let's check it. And then it says, oh, by the way, that's what it is. It sums to 1/2 times n times the quantity n plus 1. And if we go over here and look at our exam table, that's this sum right here, and there it is. So the idea in working problem 1, part B, is that you're going to be wanting to do this symbolically. Part A is a number crunching exercise. Part B is symbolically. So you're interested in being able to say, if this is what I think I need mathematically, I know I can put that in. But let's take Mathematica a little bit further, and Maxima can do the same thing, and I've got that running, but I'm not sure I'm going to be able to use it. Let's just say sum the quantity n minus k. I'll just make it a little bit more algebraically complex. I could break it apart, but hey, I'll just throw it at this symbolic computer and I'll say, can it do it? And what does it give me? So there you go. Check the math form there. It looks like the problem I said I'm going to need to work this problem. Remember? And what does it tell me? There it is. It's just gotten more complex, but we can handle it because there's the formula in terms of variables, right? So if we were working in Maxima, and we're going to be out of time here, so I can get this to open up for me. It's not wanting to open up. There it is. So here I opened up what's called a notebook in Maxima after I installed it, and I have it installed here under Windows, but I also have it available under Windows Subsystem for Linux, so I can run a Linux version of it if I want to. But similar ideas, I can say evaluate sum of k starting with k equaling 0 up to m, and I want it to simplify it for me. So when it does that, it gives me the answer, just like Wolfram Alpha did. And if I want to do n minus k, I can do that. And if I wanted to find out what those values would be for a particular value of n, I can throw that in there too. So I can say, let's substitute n is equal to 10, and I'm going to take this sum, which where did I do that? I guess I did that wrong. This was supposed to be y part. I'm probably not doing this right. I was doing this kind of early this morning. But I'm just letting you know, you can do this in Wolfram Alpha, but I don't know exactly how the language is set up there. But I can take y part, which would be this answer right here. Let's just run that again. And y part is now this symbolic expression, and what I want to do is evaluate that. Here's what I don't need. I'm going to evaluate it by substituting. I don't even think I need to do that for this. Well, I was doing something else when I was creating this. I was creating a sequence of values. I can just do this. I can just make a list of, yeah, I don't even need to do that. I don't need to make substitutions because I only have one independent variable, and that happens to be n. So I'll just have it make me a list of oops. This software, this language, yeah. It's just telling me I typed something wrong. This is compared to Python, which is a little bit more involved. Maxima is pretty user-friendly. It's very helpful about helping you find bugs. So what I did there was I said as n goes from 0 to 10, and I didn't get what I wanted. Y part is down here, it has n in it. I'm a little bit perplexed right now. I think I did something that I didn't want to do, but I can't quite see what it is. Y part is the evaluation. Put in n. I'm going to resolve this because we're out of time. Yeah, that's fine. But you're getting some ideas about what we're doing. I've got Python running in here too. I was going to do more with that, but out of time. One thing we'll need to talk about for Tuesday is office hours. Would you like to be able to meet with me before class and after class, or just before class or just after?
Either one's good with me.
Okay.
Yeah.
Maybe we'll dialogue on that on Slack.
After would be better for a lot of us, because a lot of us are in EMAC right before.
Okay. So we're going to be over there, and I don't know whether there's a space to meet. If not, I'm going to propose the signal processing lab, which is next to the lounge here, and then walk over. We'll talk about that on Slack, though. So, okay, have a good weekend.